Hello friends, I welcome you in lecture number 27 on graph theory. In this lecture we are going to discuss about isomorphic graphs. We will understand the definition of isomorphic graphs and we will explain that how to determine whether given two graphs are isomorphic or not. Isomorphic graphs means the graphs may look different in structure but they are having some properties which are common. We can see that here I have drawn these three graphs denoted by G1, G2 and G3. In all these three graphs there are three vertices and only one edge in each of these three graphs. Also we can see that there is one vertex which is having degree 0 and two vertices of degree 1 in each of these three graphs. Here I have these two vertices are having degree 1 and this is vertex with degree 0. We are familiar with the definition of degree of a vertex. Degree of a vertex means the number of edges whose end point is that vertex, or number of edges incident with vertex is called the degree of a vertex. Now these common properties give us the idea that graphs can be isomorphic, but by observing only these properties we cannot directly say that graphs are isomorphic. To check whether graphs are isomorphic, we have to establish a mapping from vertex set of one graph to the vertex set of another graph, which is bijective mapping and satisfies certain property. For example, if I want to prove that these two graphs G1 and G2 are isomorphic, then definition says that first we have to find a mapping from the vertex set of G1 to the vertex set of G2, which is 1 1 and on 2. Here vertex set of G1 graph is having 3 vertices and vertex set of G2 is also having 3 vertices, V1, V2 and V3. To prove that these two graphs are isomorphic, first we have to find a mapping from V1 to V2 which is 1 to 1 and on 2. That is the first requirement. So that is possible here. Now how to construct this mapping? So for that we have to take care that if we have 0 degree vertex, then it is mapped with 0 degree vertex. If two vertices are adjacent with each other, then they are mapped with those vertices in another graph which are adjacent with each other. So here, because we have this U1 and U2 are adjacent in G1 and here V2 and V3 are adjacent in G2. So I can take image of U1 as either V2 or V3. Suppose I am taking image of U1 equal to V2 say, and image of U2, here U1 and U2 are adjacent and I have taken image of U1 equal to V2 and here V2 and V3 are adjacent. So I am taking image of U2 equal to V3 and remaining vertex is U3. It is isolated or its degree is 0 and here V1 is isolated vertex. So we consider f of U3 equal to V1. Now it is clear that this function is 1 to 1. We can see that if we have two different elements from V1, then their images are also different. So this function is clearly 1 1. For on to what we have to check? We have to check that every element of codomain is the image of some element from domain. So here all the elements V1, V2, V3 are images of some elements of V1. Therefore this function is 1 1 and on to. In other words, it is bijective function. This is the first requirement. Second requirement is this function is constructed in such a way that whenever two vertices are adjacent in one graph, ui and uj are adjacent. Adjacent means they are joined by an edge. ui and uj are adjacent in G1 if and only if their image vertices f of ui and f of uj are adjacent in G2. That is, here we check whether u1 and u2 are adjacent or not. So here u1 and u2 are adjacent, so their images are v2 and v3, so they must be adjacent in G2. Similarly, u1 and u3 are not adjacent. We can see here u1 and u3 are not adjacent in G1, so their image is v2 and v1 must not be adjacent in G2, so that is correct. And for u2 and u3 also, u2 and u3 are also not adjacent in G1, therefore v3 and v1 must not be adjacent in G2. So if these two conditions are satisfied, then we say that these two graphs are isomorphic. G1 is isomorphic to G2. This is the symbol of isomorphic. So two graphs are isomorphic to each other if there exists a 1, 1 and onto function from vertex set of one graph to the vertex set of another graph, with such that if ui and uj are adjacent in G1, f of ui and f of uj are adjacent in G2. Now, because here I am having only 3 vertices, I am able to easily construct this bijective function. But if the number of vertices are larger or number of edges are larger, it is not comfortable or sometimes very difficult to construct this type of mapping. So in that case, we will remember some properties which are common in two isomorphic graphs. Those properties are, first property is that the number of vertices must be same in two graphs, the number of edges must be same in two graphs, and if some vertex u has degree say d, then f of u, that is image of u, must have degree d in this graph. So degrees of corresponding vertices must be same. And another properties are that if two vertices are adjacent here, then we will check that their image vertices are also adjacent. If there is some isolated vertex, here also we must have isolated vertex. Suppose in one graph we have 3 vertices of degree 1, 5 vertices of degree 2, then in the corresponding graph also we must have 3 vertices of degree 1 and 5 vertices of degree 2. So this type of properties will give us the idea that whether graphs are isomorphic or not, and if those two graphs satisfy this type of properties, those properties will help us to construct a function which is 1, 1 and onto. So remember, to prove that two graphs are isomorphic, we must have to show the existence of this type of function which is bijective. But to disprove that graphs are isomorphic, or to prove that given graphs are not isomorphic, we can show that these properties, some of the, at least one of these properties are not satisfied. Those properties are, first property is they have common vertices, vertices are same, they have common number of edges, the number of edges are same, then degrees of vertices, we have to check degrees of corresponding vertices. So as I discussed here. If one graph has 3 vertices of degree 1 and 5 vertices of degree 2, then the corresponding graph must have same type of vertices. Another common property shared by isomorphic graphs is cycles. That is, if one graph has a cycle of length 4, then corresponding graph must have a cycle of length 4. If one graph has 2 cycles of length 3, then corresponding graph must have 2 cycles of length 3. So these are the properties which are invariant under isomorphism. Property is said to be invariant if the property is satisfied by one graph, then it is satisfied by corresponding graph also. So we will remember these properties which will help us to check whether graphs are isomorphic or not. And if at least one property is not satisfied, then we can directly say that graphs are not isomorphic. But if all these properties are satisfied, then it is not necessary that two graphs are isomorphic. We have to establish the existence of isomorphism. We have to construct a mapping from vertex set of one graph to the vertex set of another graph, which is 1, 1 and on 2. This type of mapping is called graph isomorphism. To prove that two graphs are isomorphic, we have to establish the existence of graph isomorphism. And there are many functions from v1 to v2, but we have to establish the existence of at least one function of from v1 to v2, which is 1, 1 and on 2, and it satisfies this property. So I have written this definition which I just explained. They ask you to write down the definition also. And this definition is for simple graphs, that is graphs without loops and without parallel edges. The simple graphs denoted by G1 equal to order pair V1 E1 and G2 equal to order pair V2 E2 are called isomorphic if there exists a 1-to-1 and onto function f from V1 to V2 with the property that, this is important property, if two vertices are adjacent in G1, that is, if there is an edge between A and B in G1, if and only if f of A and f of B are adjacent in G2, then there must be an edge joining f of A and f of B in the corresponding graph, that is G2, and this must be true for all possible pairs of vertices in V1, and this type of function is called an isomorphism. Now we discuss one another example to check whether these two graphs are isomorphic or not. So we can see, first we will check some properties. From that we will have the ideas that whether there can be a graph isomorphism or not. So first thing we will notice is that both the graphs have same number of vertices. Here vertex set is u1, u2, u3 and u4, and vertex set of graph H is also having 4 vertices, v1, v2, v3 and v4. Now number of edges in graph G are 1, 2, 3 and 4, and here also I have to draw 2 edges. Here also we have 1, 2, 3 and 4 edges. That means graph G and H have same number of vertices and same number of edges. Now we check degrees of vertices. So for u1 we can see that u1 is incident with 2 edges, that is degree of u1 is 2, or we can say that there are 2 edges ending or meeting at u1, therefore degree of u1 is 2. Similarly, there are two edges incident with u2, so degree of u2 is also 2, degree of u4 is also 2, and degree of u3 is also 2. That means graph G has 4 vertices of degree 2. So here also we must have 4 vertices of degree 2. So we can see V1 is incident with 2 edges, degree of V1 is 2. For V3 also we have 2 edges, for V4 also we have 2 edges, and for V2 also we have 2 edges. So we can see that we have same number of vertices. You should remember this type of properties. First we check number of vertices, they are same. Then we check number of edges, they are also same. Then we check for degrees of vertices or degrees of nodes. So here we have 4 vertices of degree 2. So here also we have 4 vertices of degree 2. After that we can check for cycles if any, but these two graphs have no cycles, or we can check that there is one cycle. If we start with u1, then go in this direction, then there is a cycle of length 4. So here also we can see, if we start with v1, so this is v1 to v4, v4 to v2, v2 to v3, and v3 to v1. So here also we have one cycle of length 4, 1, 2, 3 and 4. Length of a cycle means the number of edges in the path. So here we have 4 edges, and here also we have 4 edges for this cycle, starting at v1 and ending at v1. This means both the graphs have one cycle of length 4. So all these properties give us the idea that these two graphs can be isomorphic, but by checking only these 4 properties, we cannot say that these graphs must be isomorphic. For that we have to establish the existence of function from v1 to v2 which is isomorphic and satisfies that property. That property is, if ui and uj are adjacent in G, then their image is f of ui and f of uj must be adjacent in H. But these properties will help us to construct that mapping from v1 to v2. So suppose I am interested in that function from v1 to v2. So I will start with image of first vertex u1. So what I have to take care is that here u1 is adjacent with 2 vertices u2 and u3. So I can assign image of u1 as that vertex of H which is also adjacent with 2 vertices, and it is having degree 2, but here all the vertices are having degree 2. So suppose I am thinking for v1, then I can see v1 is also adjacent with 2 vertices and degree of v1 is 2. So I can say that image of u1 is v1. I repeat again, I am assigning v1 to u1. So for that what I am checking, I check that degrees of u1 and v1 are same, and here u1 is adjacent with 2 vertices of degree 2. So v1 is also adjacent with 2 vertices of degree 2. Now I think for image of u2. So here u2 is adjacent with u1 and u4, and whatever element I will consider here, that must be adjacent with v1, because we have to take care of this property also. If 2 vertices are adjacent in G, their images are adjacent in H, and we are considering u1 and u2 here. u1 and u2 are adjacent in G, So I have to consider this image as that vertex which is adjacent with V1. Now you can see there are two vertices which are adjacent with V1. One is V3 and another is V4. Suppose I consider V3 here, then again we check U2 is adjacent with U1 and U4, that is with two vertices. So here V3 is also adjacent with two vertices, and here U1 and U2 are adjacent. So here V1 and V3 are also adjacent. So this will work. We have assigned V1 and V3. Now we check for image of U3. So here U3 is adjacent with U1 and U4, and image of U1 is V1. So here I have to assign that vertex which is adjacent with V1. So with V1 we have V3 and V4 adjacent. V3 is already assigned. So I will consider image of U3 as V4, and we can check here U1 and U3 are adjacent. Here V1 and V4 are adjacent. Similarly, we can check for U1 and U2 and U3 also. Here UT and U3 are not adjacent, so we must have V3 and V4 not adjacent in our graph. So that is satisfied here. And last vertex which is remaining, this is assigned, is V2. So we must consider f of U4 equal to V2. And we can check this property also. What about U3 and U4? They are adjacent in G. So V4 and V2 must be adjacent in H. So that is satisfied. Similarly, we can check U1 and U4 also. U1 and U4 are adjacent or not. Here U1 and U4 are not adjacent. So what about V1 and V2? So V1 and V2 are also not adjacent. So this is if and only property. If two vertices are adjacent in G, then their images are adjacent in H. Similarly, if two vertices are not adjacent in G, then their images must not be adjacent in H. So we have this function which is 1, 1 and on to from G to H. Therefore, f is an isomorphism. F is 1, 1 because distinct elements have distinct images, and f is onto because every element of V2 is image of some element of V1, or we can say that range of f is nothing but V2, which is codomain of this function. So because f is 1, 1 and onto, therefore f is an isomorphism, and this property is also satisfied. Ui and uj are adjacent in G if and only if f of ui and f of uj are adjacent in H. So both the properties are satisfied. Therefore, G and H are isomorphic. The graphs G and H are isomorphic. So in this way you can determine whether given graphs are isomorphic or not. Again I summarize whatever I have explained. To check whether two graphs are isomorphic or not, we have to first verify all these properties which are invariant properties for isomorphic graphs. First we have to check whether graphs have same number of vertices and same number of edges. Then we can find degrees of each vertex in both the graphs, and we can check whether corresponding degrees are same or not. In other words, suppose one graph has this type of degrees 2, 3, 4, that is there are two vertices of degree 1 there are 3 vertices of degree 2 and there are 5 vertices of degree 4 in one graph, then in another graph also we must have same structure. Suppose here you have 3 vertices of degree 2 and here you have 2 vertices of degree 2, then you can directly write that graphs are not isomorphic. So in that sense you have to check degrees of vertices. After that you can check if both the graphs have any cycles or not. Suppose one graph has cycle of length 3, then another graph must have cycle of length 3. Suppose one graph has 4 cycles of length 2, then corresponding graph must have 4 cycles of length 2. If there are 4 cycles of length 2 in one graph and here suppose there are 3 cycles of length 2 in another graph, then also you can write that graphs are not isomorphic. So this is very interesting topic, and we will be continuing with more examples in upcoming lectures on isomorphic graphs. Thanks for watching.